Hi there. Final take on this, good, bad, or ugly. This lesson or video is meant to be embedded inside a larger lesson on transformations. So if you just clicked on this video out of the blue, know that there is a larger lesson that goes over some of the vocabulary, the notation applications, and summarizes everything that we're about to look at on Desmos. What we're going to do in this video is explore what are called transformations. And we're going to look at this in the context of quadratics. So I have over here f of x equals x squared. This is called the parent function. It is the simplest function inside this family. The coefficient of the x squared is a 1. You can tell that because when I put a 1 in front of it, it does not change the graph. And this graph over here is what's called the parent graph, meaning it is the graph of the parent function. And what we're going to look at is how does adding, subtracting, multiplying, throwing negatives in, like what does that do to this particular graph? So we'll start with f of x is equal to x squared, okay? And you can see that the red graph is laying perfectly on top of the black one. And what I'm going to do is add plus 2. And what you should notice looking at this is that the graph slid up 2 units. And what I tell my students to look at is to look at the vertex. If you look at the vertex of the parent function, it was at 0, 0. If I look at the vertex of this new function, it is at 0, 2. And so essentially adding that 2 took the graph and it slid or translated the graph up 2 units. Now, once in a while, I will have a student say, well, it also made it narrower. Well, it looks that way, but remember that the parabola is narrower at the bottom than it is as you go upward. And so by sliding it upward, you're just sliding that narrower part upward, but you didn't actually make the parabola itself more narrow. All right, so that made it slide up 2 units. Now, we might see the connection there, like, okay, plus 2 up 2 units, but because this is easy to do on a computer, I'm just going to go ahead and change that plus 2 to a plus 4. And we can see that that seems to hold pretty consistently. The parabola has now gone up 4 units. And you could do this a whole bunch more if you wanted to. You could put in a plus 3 and see that it goes up 3 units, or a plus 5 and see that it goes up 5 units. And you could keep going. Typically, like we could do a decimal plus 4.5 and see, oh, look, it went up 4.5 units. So usually students don't need to see that though. We get, okay, if I take the parent function and I add something to it, I can slide the function up. And so the next thing we might ask ourselves is, okay, well, what if I subtract? If I subtract, that seems like it should make the function go down. So we'll try that. We'll do a minus 3, and notice it did not make the parabola wider. It simply slid the parabola down. So now we are at 0, -3. And then as we do that, we're sliding that narrow part down, which means that you have wider parts up here, making it look like it's wider, but it's just because we slid it down. And I'll sub that out. We'll do a minus 5. Okay. And we suspect at this point, okay, well, the parabola is going to go down 5. And it did. Okay, so we can see down there, it's 0, -5. And so what we can see is that adding or subtracting this number to the function is sliding the graph up and down. Now, the way I summarize this in the lesson, and I want to show you this, is that adding or subtracting a number outside of the squaring. Now, what I mean by that is that you've got the squaring and your adding or subtracting is happening independent or outside of the squaring. And it doesn't necessarily mean after the squaring. Okay. So this is what I want to show you. So I did not mean to get rid of that. So typically we would write x squared plus 5, but there's nothing about this, like adding it outside, that says that it has to be after. So you could add it on the other side. Okay, and you'll notice that the blue and the green are right on top of each other. So if I turn off the green, you can see the blue is right underneath it. Okay, and so what we mean by that is the 5 is being added outside of the squaring, whether or not that is happening on the left or the right. So we're not thinking left of the x squared and right of the x squared. We're thinking outside of the x squared. And the same is true for subtracting. So if I were to subtract a 5, okay, what that would do here is make that 5 negative. And you can see, I'll turn off the green one again so you can see, oh, the blue one is right underneath it. Okay, and you might be a little bit thrown off because you still see a plus sign there, but remember that x squared minus 5 is really x squared plus negative 5. And so when you switch the order, the negative is going to kick over with the 5, meaning that the 5 is still negative and the x squared is still positive. So they're going to retain their sign. So the first piece of this demonstration is adding or subtracting something outside of the squaring will slide it up and down. So the next one we explore is this. We are now going to add or subtract inside the squaring. And you might be like, what does she mean by that? That's what I mean by that. And just for funsies, I'll put the other one right underneath it. Okay. So we've got x squared plus 2 outside. So we're adding the 2 outside, and that was what made it go up. And adding it on the inside, so inside the squaring. So we're taking the plus 2 and we're squaring that all along with the x. That actually slid it left too. You might say, oh, I really thought that should have been to the right too, because positive was up. So positive should be to the right because that's the positive direction. And that's one of the most common mistakes that we make because it is backwards. Now, what I could do is show you that. I'm going to get rid of that. Show you the table for that. And essentially what we could do to justify this is we could go and plug in the numbers. So if I plug in x equals -2 right here, -2 plus 2 is 0 and 0 squared is 0, which means that, yeah, like that went left 2. It's -2, not +2. That will make that equal to 0 over there. So it does slide it to the left. Now, if that is the case, then if I add 4, like I did before, except I add it inside, then I would expect it to go left 4. So I'll just delete the 2 and put in the 4. And there we go. So it went left 4. So adding that number inside does slide the graph to the left. So thinking in terms of, okay, well, math is consistent and there are patterns. So subtracting it probably will make it go to the right. So let's take a look at that. We'll do -3. And we are confirmed. So the vertex, again, we want to watch that vertex. Vertex went to the right 3 units. And just to make sure that our pattern holds, we'll try the -5 and it should go to the right 5 units, and it did. And so the summary statement for that is adding or subtracting inside the squaring will slide it left and right. So you've got different places where you can add and subtract. So if I do this, so right now it's going to the right 5. Well, if I do a -5 on the outside, now it goes to the right 5 and down 5. So you can see the 5 there. I think it's probably, I can see it just fine. I think it's probably right on the bottom of your screen. So it went right 5 and down 5. Okay, and so you can slide the parent function up and down and left and right. Next thing we're going to look at is what happens if I put a negative in front of it. So we'll have y equals f of x, and now we will have negative x squared. And you can see that that flips it over. So that negative takes all these positive coordinates. So let's see if we can find that point right there. So that is the point, I believe 2, 4. Okay, it's like a little hard for me to get right on the point, but is the point -2, 4. And when you flip it over, it now becomes negative. Oh, I had it there for a second. -2, -4. So it takes all of those y values and puts them on the other side of the x-axis. So it flips it over. Now, you can also do a different kind of flip, okay? So this is a negative on the outside of the x squared. And if I were to convert that over to a table, it is not letting me, and I don't know why it's not letting me. Try to define f. You've defined f in more than one place. Oh, okay. I turn that off. There it goes. Okay. It was not behaving there. So you can see that we have -2 and -4. I'm actually gonna do something here. We're gonna do f of x is equal to x squared, and then down here we'll call this g of x. Okay. That way we're naming it something different. So if I create the table for that one, and then create the table for this one, you can see that what it did. Oh, I want to create the table for that one. There we go. Is it flipped all the x's over. And so +4 now is a -4. +1 is a -1. 0 is still a 0. And you can actually see the points over there. And so that's called a reflection. So it reflected it over the x-axis. Now, this is dangerous for me to do in a video, but I mean, what's life without a little risk? You can also flip it the other way. And that would be by putting the squaring inside. And the reason we don't talk about that too much in math class is because you can't see the flip. So you cannot see like that this point got flipped over here. Now, here's what the risky part is. I think the table like won't show it because like all the y values are the same. It might be able to see it if we did put a slide on it first. But you can't see that flip. There is a flip happening there, but the flip is over the y-axis. And what happens is this point just gets flipped over to here, and so you don't see it, so you just kind of have that mirror image. There are some functions where you can see that flip, and so usually in my classes I don't talk about that flip until we get to something where you can see it a little bit better. All right, so that brings us to, well, what about multiplying? Okay. So what if I multiply it by 2? And this one actually did get skinnier, okay? So there's a lot of different ways teachers might describe this. I've heard people say, oh, it got narrow or it got skinny. A better way of saying it is we stretched it vertically. So if you think vertical is your up and down, and picture the parabola as being some kind of rubber band, and you're pulling that rubber band. And so as you pull the rubber band, it does get narrower as you're pulling it vertically. It is a vertical stretch there. If I change the 2 out front to a 5, it should essentially stretch it even more. Now, these get a little bit dicier to deal with. They're harder to see. It's a little bit harder to find points on there, and they get a little bit harder to compare. So sometimes it might be a little bit hard to see, well, did it really get narrower? And you actually need to kind of graph them all at once so you can see, oh my word, like, yes. And so if I put like a really big number in front, we'll do like 100. Okay, you can tell that parabola is getting really skinny. It's like we're really, really, really pulling on that rubber band there. Now, remember earlier, I said that the number in front of the x squared was a 1. And so as we are getting numbers bigger than 1, we are stretching it. So now we might want to look at, okay, well, what happens if I have a number less than 1? What if instead of a 2, I have a 1/2? And what you can see here is that it got wider. And so we might say it's wider or it's fat, or but the best way to describe it for most Algebra 2 students is it is compressed. It's like somebody is pushing down on it vertically. Now, it's a little bit hard to see there, but let's say I put in like a 1/10. Okay, now you can definitely see that, okay, that's getting wider, and it's like somebody's pushing down on it and making the parabola wide. If I were to go and put in a really big number, we'll like put in the 100. Now it almost like is starting to look flat in comparison. It's got like a little bit of a curve to it. And what you're looking at is like the bottom of a really, really wide parabola. If I were to zoom way, way, way out, you could start to see, all right, that is still a parabola. But notice what my window is here. I'm going out to like 500 and 600 to be able to get that parabola-y kind of shape. When I zoom in, it looks flatter, and that's that compression. Okay, so last kind of thing that I wanted to cover in this is you can combine all of these together. So you could have one transformation, two transformations, and so forth. So if I take, say, my 1/, we'll do 1/10. We'll do 1/10. And then I say, well, I'm going to make that negative. It'll take that and flip it over. So when we say less than 1, what we really mean is less than 1, but like greater than 0. Okay, because as soon as you put the negative, now you're dealing with something else. Now you're flipping it over. So we would say this one was reflected over the x-axis and also compressed. And if you want to be specific, say compressed by a factor of 1/10. Factor meaning things that are multiplied. So you could see something like this. Okay, so we can put all of them in here. So we'll put a negative and then a 4, and then we'll do x plus 6 all squared. And I don't know, let's make it go up 4 units. Okay, and so we've taken the same basic shape. The negative is what flipped it over. Okay, so you can see it's flipped over. The 4 made it skinny. Okay, it's got that stretch applied to it. The plus 6 means it went to the left 6. And then the plus 4 outside means it went up 4. And that's an example that has all of the transformations, but you can see any number of them. So we could do the same thing, and I could get rid of the plus 6. So now it doesn't have that like left. It's not moving to the left at all. I could move it to the right, or I guess I moved it back to the left, and I could get rid of the vertical. So like, no, we're not going to slide it up. I could make it go down 3, and I could get rid of the skinniness of it by getting rid of the 4, or I could flip it back up by getting rid of the negative. So all of those things contribute to what are called transformations. To some extent, you can explore them on Desmos. Pretty easy to do what I did. And then you kind of have to memorize them. You just need to handle them enough to remember what the different numbers and signs do so that you can graph things quickly or determine how one parabola is related to another. So thank you for joining me on this. If you were coming from the transformations video, go ahead, click back over to that for the summary of this demonstration.